Alright, so the next part, you're going to need a couple pieces of tape. They change the names of the tape every year, but I'm going to go with the names right now. The first piece of tape is, I'm going to call it the base tape. And you put it down on your table, desk. The next tape that you're going to put down, I'm going to call the bottom tape. You put it on top of the base tape. Then you have the third piece of tape, which I call the top tape. It's good to fold these over a little bit so they're easier to get off. So this is where the magic happens. So I'm going to pull the top tape off, kind of fast, but not really fast. Of course, when you demo this, it never works. The bottom tape off. So you can kind of see that they don't like being near each other. Okay. So you should see it something like this. So they're repelling each other. And that's because they're oppositely charged. All right, and this is the idea behind the electroscope. So this is an actual electroscope. It has a piece of gold foil in there. And if you add charge to it, what you'll see is that the gold foil will be repelled. Okay, why is it being repelled? Yeah, so they have the same charge, so like charges repel. And so, because of the amount of charge on the tapes, you can determine how far they're going to be apart, right? More charge, more force, farther they are apart. So we can turn that around, and we can say if we know the distance between them, we can measure the charge. Okay, that's what we're going to do in this part. So here I drew two pieces of tape. There's I'm going to call this the distance between the centers of the tape, which means that this is 2D. The tape has a mass, also has a charge on it, and it has a certain length. What are the forces acting on the tape? What is it? Good, force of gravity. So I'm just going to analyze this piece of tape that's near on the other side. F sub g, force of gravity, and the other forces? The electric force. Which way is the electrical force pointing? So they're repelling. Call it the Coulomb force. Any other forces?
Stuck together at the top, so.
So they're stuck together. So is this tape moving? Ideally not, right? It's just static there. So in order for this tape to not be moving, the sum of the forces has to be equal to 0. So there must be a third force per these two forces. We're going to call that tension. So those are the three forces acting on that tape. One other thing I want to point out is that there's an angle here. I'm going to call that theta. Alright, so before we start analyzing the forces here, we have basically x and y, right? Two coordinates. And so we're going to need to use this angle. So we're going to need trigonometry. So let's review trig real quick. So what's that acronym we use when we're doing trigonometry? SOHCAHTOA. What does SO stand for? The sine of the angle is equal to opposite over hypotenuse. What is cosine of the angle is equal to adjacent. the last one, tangent of the angle is, I'm going to go right over the wrong, that's all I know, right? But it's also opposite over adjacent. So the first thing I want to analyze is how is theta related to d and the distance L, the length of the string, or the length of the tape. Any ideas? Well, let's just start going through our trig and seeing what happens. Let's start with sine. Sine of the angle theta is opposite. So this is 2d, so half of that is 1d, right? Actually, let's do this a little differently, sorry. I'm going to call this d, because this is what we're actually measuring. I'm going to call this d over 2. I like that better. Doesn't really matter, but I think it makes it cleaner. So this is d over 2 now, because this is half this opposite distance over, what is it? What is the hypotenuse? So that means that theta is equal to sine inverse d over 2 over L. Put that in your calculator, you can calculate. There'll be some angle, so it'll be in degrees for us. We use radians, but degrees are sometimes easier to work with. And 15 degrees, 20 degrees, depends on how much charge, right? If you have more charge, you're going to have a bigger angle. Great, so now we know theta. Let's analyze the forces. So what law do question? What law do we use to analyze forces?
I don't know. I was just trying to
Newton's second law. What does Newton's second law say? Force equals mass times acceleration, but it's really a vector, and we need to remember to add up all the forces. So this is something you guys are going to get really good at doing. Newton's second law. All right, so this is really two equations. It's an x equation and a y equation. So what are all the forces in the x direction? So this is the x direction. Can we name our force? Is this guy in the x direction? Yeah, so let's put him there. And he's in the positive x direction, so let's make him positive. That's the Coulomb force. Is tension in the x direction? Yeah, there's a component. There's a component in the x direction. It's also in the negative direction, so I'm going to put a minus sign there. There's a tension, and then there's some kind of trig function. Is it sine or cosine? Sine. So you can go through the trig and figure that out, right? It's not difficult to do. That. Let's see. Well, I'll tell you the way I think about it. I say, what happens when the angle is 0? So if the angle is 0, this guy is all in the y direction. There is 0 component in the x direction. So what happens when this guy is 0? Sine of 0 is 0, and there's nothing in the, there's no tension in the x direction. That's how I do it that way. I don't actually use this. But if you want, you can go through this way and prove that this guy should be sine. And what is it equal to? MA. Right? Is this guy moving? No, so 0. Acceleration is 0. It's not accelerating. All right, let's do the y component. So the y is this direction. Is there any forces in the y direction?
Gravitation.
Gravity, right? So just the gravity. Putting over here is a minus f of g because he's in the minus direction because I picked up to be positive. And then there's a tension, right? And it happens to be cosine of theta because we already moved sine theta the other direction. And the way you can check that is if the angle is 0, cosine of 0 is 1. But equals 0 all detentions. It takes a little practice, but you get used to it. And what does it equal? Is it accelerating? No. All right. So we applied Newton's second law, we identified the forces, and we summed them up, and we set them equal to MA. Congratulations, we got at least 6 out of 10 points in the exam. All right, so now I'm going to do something a little weird, because I know how to get the answer algebraically very fast. And that is, I'm going to move this guy to the other side, and move this guy to the other side. So I'm going to say t sine theta equals fc. Everyone see that? And then t cosine theta is equal to what? F sub g. Now I'm going to divide them by each other to get rid of t. So I get sine over cosine, but that's tangent. Is equal to fc over f sub g. I'm going to box this one because you're going to need this one to do some calculations. And then I'm going to box this one. All right. This gives us the ratio of the two forces as a function of theta. All right, but why do we want to do all this analysis on forces for? What were we trying to solve for? Do you remember? So what happens is you do these calculations and you sort of forget what you were doing halfway through. So I like to remind myself what I was trying to do. We were trying to find the charge, right? So where is the charge here? He's in here, right? He's in the pool. All right, so let's write the charge in there so we can see him. I'm also going to move f sub g, which happens to be mg here, mass times gravity, acceleration due to gravity. So I'm going to write mg tan theta, and over here is this guy, which is k, and I'm going to write q squared. Why am I going to write q squared? Because I'm assuming that they have equal amounts of charge. All over r squared. What is r squared here? Is it d? The distance between him is d over 2. Squared.
Why is it at that point instead of at the other point?
Why is it
Well,
in the
because-
middle?
Yeah.
All right, so we made a little bit of approximation here. We assumed all of the mass and all of the charge were at the center of the tape. It's a pretty good approximation, but it's not entirely true. But we're just trying to estimate how much charge is on the tape. We're not trying to get, 6 decimal places accuracy, right? We're just trying to get a good amount of number for the charge. All right, so we can solve this algebraically for Q, and then we're done. So what is Q? It'll be d over 2 square root mg tan theta over k. I think that's right. I skipped a bunch out. I did like 4 or 5 algebra steps in a row, so you should check that. I don't guarantee you that I did my algebra right, but I think it's right.
D over 2 should be squared.
Did I do it wrong?
Should D over 2 be squared?
Yeah, but I pulled it out.
Oh,
Okay. So double check it, make sure it's right. I think it's right. So what does this say? If we knew what D is, which we do because we're going to measure it with a ruler, and if we knew what the mass was, which we can weigh it. By the way, it's not very easy to weigh the tape. So you're not actually going to weigh the tape. What you're going to do is I'm going to give you lambda, which is the mass per unit length, which happens to be 0.0014 kilograms per meter. So what you're going to do is you're actually going to take the length and multiply it by this and get the mass. It's easier. Is that kilograms per meter? Kilograms per meters.
Can you stick that number again?
Um,
Can't read it.
0.0014. And so you'll know the mass. G is what? 9.8 meters per second squared. Tangent of the, you'll have the angle, because we're going to measure D and L, the angle here. And K is right here. All right, and the last part, we'll ask you to, once you know the charge, is calculate how many electrons that is. How do you do that? You know the total charge. Can you calculate how many electrons there are on the tape? Yeah, divide by the charge of an electron. Any questions?